Okay, so we'll have our first exam the week of October 23rd to 27th, so it's not next week, but the week after. I'll give it on Dropbox. You can log in anytime during that week and take it. Once you start it, you'll have 75 minutes to take it. There's 15 questions, multiple choice, open book, open internet. Okay, it'll cover system Verilog, RISC-V, instruction set architecture, and RISC-V microarchitecture. Under System Verilog, it's basically behavioral and structural HDL, syntax. For RISC-V instruction set architecture, it'll be just writing small snippets of code or analyzing small snippets of code, instruction encoding. And then for the microarchitecture, it'll cover the 3-stage pipeline. Okay, any questions about that? I've got example exams on Dropbox you can check out. Yes?
So does that mean like at the latest it'd be due with the no weekend penalty on like the 29th?
No, actually this one is, it'll open up on midnight on Monday. It'll close midnight on Friday. So you just, you'll have to, it doesn't have the same late penalty rules.
Okay.
So it's just Monday through Friday. Okay, so we assigned lab, let's see where we at here. We assigned lab 3. That's due October 13th, so the end of this week. And then we'll be assigning lab 4 next week.
Is it due Friday or Sunday?
Sunday, yeah. It says Sunday, but it should be Friday. Effectively Sunday because it's late penalty. Yeah. Okay, so
is lab 4 the one that's kind of like optional, depending on how we did on the labs?
that's right. Yep.
Choose to not do final exam, choose to not do project 4, one or the other.
That's right.
It's awful.
Wait, there's a syllabus?
Oh,
There's always a syllabus.
They definitely did not give us a paper copy for exam. But the class is great.
Okay, so lab 3. Any questions about lab 3? Is that going pretty well? So the objective here is to design the RISC-V processor that can execute the instructions listed here. These are basically just arithmetic, logical comparison, and the one I/O instruction. So there's no branch and jumps, and there's no loads and stores here. This minimal set of instructions, 22 instructions, should be enough for you to write a practical program that will allow you to enter a number on the switches on the DE2 board and have it do a binary to base 10 conversion. And then output the base 10, the decimal number, on the hex display. So you'll be using your 7-segment decoders for this. So we talked about the RISC-V instruction formats. We're only using 3 of them for this lab. So the 22 instructions that we're targeting span these 3 encoding formats. And actually, it's really just 2 encoding formats because the U type is only used by the one instruction, the LUI instruction. Yes?
Like, I understand that we have to kind of assign and define like the R type, I type, U type. Can we do that all in the same file, or does that have to be done in multiple files?
You can do it all in the same file. Okay. Yeah, that's up to you how you want to organize the Verilog, how you want to break it down into like submodules. And
do we kind of like assign the R type the same, or assign the I type the same way we do the R type? Or are they all like you have to define one?
So I have I think I have a figure about that here. Yeah, that was about what I was about to explain. So the instruction memory is a RAM, and it'll spit out the instruction, and then you can take the instruction into a block called a decoder. That can be a module that's in a separate file if you want, or you can just inline it. You can just make that decoder a snippet of code inside the CPU module, and the decoder can basically just rename pieces of the instruction. So for example, you can bring out the opcode, the function 3 field, the function 7 code, the CSR field, and immediate 12 field, right? The CSR field and the immediate 12 are actually the same bits. It's the upper 12 bits of the instruction, but there's 2 signals here declared just so it's more clear. What's going on?
The I type doesn't have a font 7, I think.
Right. Well, yeah. Yeah, that's a good point. So there's no func7 in the I type, right?
That's what I was wondering, because can I change like the output of a module on the fly?
Well, realistically, what you can do is you can output a whole bunch of shit and just not use it.
Yeah, exactly.
Oh.
Yeah, exactly. So the
That's pretty
I,
much how I have it set up now. I just didn't think that would work. I was like, all right.
that's right. So the I type has an immediate 12 field, which will be actually the immediate 12 field will be equivalent to the func7 and rs2.
Yeah.
Like concatenated together. But you can have three signals in the CPU. One is immediate 12, one's func7, one's rs2. But you'll only use the fields that are relevant for that instruction, like he said. Yeah, so you can ignore, some of these will be don't cares.
You can basically just do the whole module, just do one big long string of signs, just assign all of the different bits, different things, and if you don't need it, just don't use it. If you do need it.
Right. Yeah, so the control unit will be you can design it like as a big if then else. And if you don't consider something in the if then else, then it's ignored.
Yeah.
So
I
don't
think that
care.
For the R type, it was just a little more confusing on the I type, but it's cleared out.
Okay. Yes.
So in system Verilog's for the outputs, yeah, for the outputs declared in the module, you don't have to give all those like declared. So like you can just list all of them and it's fine, you don't have to all of them. So like if you have like all the different like func7 or 8 12 in the same module output, you don't have to use one together, it doesn't matter.
That's right. Yeah. That's right. I think I don't remember if I included that. So where did I put that?
I wish I just been in the
I thought I had a lab hex RIU. There it is. CPU.sv. Okay, so yeah, so this is actually the code, the decoder code right here. So I just used the signs in here to break these signals out. So for example, func3 is instruction EX14 down to 12, right? And then in the control unit is just an if then else. And in this case, I'm looking at the add instruction and the add I instruction, right? So the add instruction has the func7, right? Whereas the add I instruction doesn't have func7. So you can see that here I'm looking at func7. I'm testing to see if func7 is 7 zeros. Whereas if this condition is false, then it will check this condition, which actually only looks at opcode and function 3. You see, so basically I'm ignoring function 7 in this case if it in this second if condition. Make sense? So if it is an add I, then you're right. Function 7 doesn't exist, but I'm not testing it either. So it's a don't care. Yes.
So does the control unit actually end up being like 22 instructions that we have to do?
Right.
So basically it's just 22 if else.
Yeah.
Statements pretty much.
Yeah, that will change in the next lab for the branches, because the branches will not only check to see if it's a branch instruction, but we generally handle branch resolution in the control unit too. So there'll be like two if tests for the branch, one for the whether it's taken and one if it's not taken, right? But in this lab, yeah, I think there's one of these lines for each instruction. Actually, no, CSRRW, that's an exception. CSRRW is one instruction, but you'll need to have 2 lines in here for that. One for the output to the hexes and one from the input from the switches. And that will depend on the control status register, whether it's 0 or 2. Make sense?
Yep.
So there should be, I think, 23. Well, then you want to have an else that's like an unknown.
Yeah.
That's like a default. That would be like an invalid instruction case where the control unit doesn't know what the instruction is. Okay, any other questions about the lab? Okay, so is the CSRW instruction clear? Does it make sense? So this is our IO instruction. So this is an I-type instruction, and the immediate 12 field is used for this, what do they call it? The CSR address. So you get 12 bits in there to specify an address. In this lab, that address will only be 0 or 2 coming from RARs, unless your code in RARs is, something's wrong with it. As long as your code in RARs is good, whenever you have a CSRW instruction, the immediate field will either be 0 or 2. If it's 0, that means you want to read from the switches, and if it's 2, you want to output to the hex displays. So this is the code. This pseudo code is from I got that from the RISC-V official spec. And what it's supposed to do is exchange the CSR register with the general purpose register. It's supposed to do a swap. It's supposed to take the CSR contents of the CSR register, put it in the general purpose register, and the general purpose register contents go into the CSR. That's not how our processor will work. In our case, we're going to hack it a little bit. So when you access register 0, it only reads the switches, and if you access register 2, it only writes the hexes, right? Because it doesn't make any sense to put a value into the switches because that's strictly an input device, right? So that'll all be that behavior will be encoded into that control unit if state, that big if then else. Okay. Okay, and then I mentioned that your 7-segment decoders are going to come in handy here. You'll have the CPU.SV that will be instanced. The output of that will be a 32-bit output, which will be sent to your 7-segment decoders. And then that will all be in your top.sv, and then your SymTop will encompass the top, right? So SymTop is your test bench. And in this lab, the test bench doesn't really do a lot. It just drives the clock signal, and it pulses the reset. And you might say, well, I thought you said that the test bench is supposed to check to see if the design is working. The only way to know if it's working is to look in the register file. So you simulate it and you look at the register contents and you just check what values are going in the registers. There's probably a better way to do that, but we haven't discovered it yet. I mean, one way to do it would be to test with small segments of code that use the CSRW instruction to push values out, and then the test bench could check that. So for example, you could add 1 plus 2, and then you could then take the sum and bring it out to the hex displays, right? Then the test bench, the SymTop, would be able to see those because it could read the hex displays, and it would know if the add instruction worked. The problem with that is that if it fails that test, you don't know if it was the add instruction that failed or the CSRW instruction that failed, right? So it's easier in this case just to look at your register contents. Okay. We talked about the pipeline. So there's a 3-stage pipeline. So once the pipeline gets filled, there's always 3 instructions in flight, in progress at one time. You'll have an instruction in fetch, an instruction in what we just call execute, the middle stage, and then an instruction in write back. Does that make sense? So the instruction in fetch, you don't really see it because it hasn't been fetched yet. There's nothing to look at in the fetch stage. The only thing you can look at is the program counter. I think that's it, right? Yeah. There's just the program counter, the address of the instruction being fetched. That's all you've got. That's the whole fetch stage. In the execute stage, you have the inputs and outputs of the register file, the inputs and the outputs of the ALU, and the inputs and the outputs of the control unit, all in the execute stage. And then in the write back stage, you've got nothing other than just the write port on the register file. You guys with me on that? Does that make sense? So in other words, most of the signals are in the execute stage, but you have these 2 other stages that you don't have as much going on in those 2 stages. Okay, so then we looked at some, I think last time, so I think this is the whole design. I'm pretty sure I've got everything in here now. Little tough to read this because there's so much going on here. I usually show the CPU as like two halves. Like I usually show this design and this one, right? Like on the test, that's usually how I show it on the test. I show it like this, where you've got kind of this part of the CPU and that part, instead of mashing everything together. But in this slide, I try to combine everything just to give you an idea of all the pieces that are in there and how they're connected. So you've got the instruction memory program counter. Program counter is just a counter. In this case, it just counts up by 1 every cycle and also has a reset, a synchronous reset. Control unit is just a big if then else. You can make that a module if you want. Probably should, because otherwise this file gets pretty long. But that's up to you. The register file we give you, that is a separate file, and the ALU we give you, and that's a separate file. And then these dark gray squares are just flip-flops / multi-bit registers. Multi-bit flip-flops, which I refer to as registers, right, usually. They just delay a value from one cycle to the next. And then there's the sign extend, and that's a combinational logic, and there's 2 multiplexers, those are combinational logic. Those could be made with just like an assign, like one assign a statement, right? Make sense? So you guys remember the sign extend. The reason the sign extend is there is because if you're executing an I-type instruction, you have to take the immediate and sign extend it. So you take bit 11 of the immediate and you replicate it 20 times, right? So you have to copy the sign bit 20 times, because when you take those 20 copies and you combine it with the 12-bit immediate, you get a 32-bit value, because that ALU is a 32-bit ALU. So it converts a 12-bit value to a 32-bit value. The multiplexer is the element by which you establish data paths through the CPU. So the multiplexer allows you to like steer data around. So this multiplexer is used to control what value is getting sent back to the register file, and this multiplexer is controlling what value is getting sent to the ALU B input. So this is actually a lot simpler than the MIPS CPU, because then in the MIPS CPU you had a multiplexer here too. Because in MIPS there was 2 possible destination register addresses. You could use the RT or the RD field, depending on if it was an R-type or an I-type instruction. So that's gone. There was also the sign extend might 0 extend on a MIPS CPU, but in RISC-V we don't do that anymore. It's just everything sign extend, so they simplified that. And this mux here is only as complicated as it is because of the CSRRW. We had to add this IO0 in and the LUI, and of course the ALU out, right? ALU out. So this multiplexer controls what goes back to the register file, and there's 3 options. There's the IO0 in, that's the switches, that's the main input. That's one option. You use that for the CSRRW instruction when you have IO address 0 in there. Then there's the load up immediate, which is that weird instruction that just loads a 20-bit immediate into a register. That's the only U-type instruction we have. And then there's the normal case, which is where the ALU output goes back in the register file. That's for computational instructions. Logical, arithmetic, comparison, shift. Make sense? So basically, this guy is always going to be set to 2, except if it's a CSRRW, in which case you set it to 0, or if it's LUI, you set it to 1. But it's almost always going to be 2. Okay. Also, here's another example of that. The write enable input on the register file, that tells the register file to write. That's going to be 1 in almost for every instruction. I think the only exception to that would be for the CSRRW instruction when you're writing the hex displays. You don't write a register in that case. And if you read an instruction, you don't know what it is, an unknown instruction, then you should set that to 0 in that case. But in every other case in this lab, that reg write signal coming out of here will be set to 1, and then this register just delays that by 1 cycle, so it pushes that into the write back stage. Does it make sense? Okay, so what that means is that these guys, these little dark blocks are just always at pos edge clock, output equals input. That's it. The muxes is in a sign with a ternary expression in it, and the sign extended is in a sign with a bit duplication operator in it, right? And then all these wires are made just by through the names of the signals. All these connections are being done, established through using the same name as, like, say, an input and an output on different pieces of the code. Okay? Any questions? Okay. So then I have a few slides that show some examples of the control unit code. And the quiz also had some questions on this, and I'm going to go back and review the quiz too after this. But in this case, we were looking at the add, subtract, multiply, and SLT. These instructions are all identical, except I think the only difference is the ALU op that's used. What you tell the ALU to do. Aside from that, they're all the same. So the ALU source for all 4 of these instructions is 0. And remember, the ALU source is the one that's controlling this mux. So the ALU source is 0 because all of these are R-type instructions. There's no immediate. So this ALU controls whether we're sending a register or the immediate in the ALU. So that mux should be 0 for all 4. Reg select should be 2 for all 4 because the value being written back is coming from the ALU. Reg write is 1 for all 4 because all 4 of these instructions write a register. And the GPIO write enable should be 0 because that's only set for the CSRRW when you update the hex displays, right? So out of the 5 control signals, 4 of them are the same for all 4. The only one that's different is the ALU op, which for that you have to look in this table to figure out what you have to set the ALU op for whatever you want the ALU to do. And the ALU in this case is just doing whatever the instruction mnemonic says to do. So, add, subtract, multiply, or set less than. Does that make sense? Okay, so on the next slide, I have some I-type instructions mixed in. So there's 2 I-type instructions. There's an AND I and a set less than I. And so these guys are going to be different from the other two instructions that are R-type. I think they're only going to differ in the ALU source, right? So the I-type instructions will have an ALU source of 1, and the R-type instructions have an ALU source of 0, because R-type you want to send in the register as the second input on the ALU, and for I-type you're going to send in the sign extended immediate. And then the reg select is the same for all of them, the reg write is the same for all of them, the GPIO write enable is the same for all of them, and then the ALU op is just going to depend on what you're doing. So the and the and I both have the same ALU op. It's 0, 0, 0, 0 because that's how you tell the ALU to do a bitwise and. The set less than and the set less than immediate both have the same ALU op, right? 1, 0, 0, 0 because that is the shift left, right? Shift left operation. Okay? And then I think I've got one final, so now we've got some kind of miscellaneous instructions. We've got LUI, and there's 2 versions of the CSRRW. And like I mentioned, this is why you're going to have 2 if conditions for the CSRRW. So you notice I have two rows of this table for that. So the LUI, actually, all 3 of these don't use the ALU at all. None of these 3 instructions use the ALU. None of them require an ALU operation. So I've got the ALU op set to X, don't care. Or you could just set it to 0, so it doesn't matter. ALU source, likewise, is also don't care. ALU op is don't care. ALU sources don't care because if I'm not using the ALU, I don't care what the ALU op is or the ALU source because the ALU op defines what you want the ALU to do, and the ALU source tells it what input should go in the ALU. In both cases, those are all don't cares. The reg select is the relevant control signal here because the LUI, you're going to want to set the reg select to be 1, and this is a little hard to follow here, but what's happening here is if you go to that reg select mux, that's this guy. Now you might say, wait, why did you put the reg select mux all the way to the right when it's controlling what's going in the register file, and that's all the way to the left-hand side? Because it's like data flow. Data flow kind of flows from left to right in these diagrams. So notice that this mux, where's my mouse cursor? This mux, the output of this mux kind of feeds back all the way to the other side of the diagram, which is confusing, but it's meant to represent that this is the final place data goes, is on the right-hand side. But because the register file provides inputs and also accepts the outputs, you have to choose where you put the register file. So the register file is on the left, the mux that controls the inputs of the register file is on the right, and that's why you've got this feedback going back. You guys see that? That makes sense? So this mux, if you tell this mux to select input 1, it comes from another crazy wire that originates all the way to the left, and it's instruction EX31 down to 12 concatenated with 12 zeros. So what is that? That's the immediate 20 field from the U-type instruction. It's the upper 20 bits immediate field, immediate 20, and with zeros attached to it, right? Concatenated. Or if you rename that signal using the decoder, you might just call it immediate 20, right? One or the other. If you're lazy like me and you didn't do the decoder, then you would just refer to it as the upper 20 bits of the instruction EX. If you put in that decoder, then you would have renamed it immediate 20 EX, right? You'd have a little special name for that. So for the LUI, the reg select should be 1. And then for the CSRW, where you're reading the switches, you're going to want to take input 0, because that's the GPIO in, which is badly named, because in an earlier diagram, I referred to it as something else. What did I call it before? I called it, okay, in an earlier diagram, I called it IO0 in, and I have an IO0 out, right? I forgot to change this. Does that make sense? So IO0 in is just attached to the switches on the FPGA board. IO2 out is connected to your 7-segment decoders, right? If you go back to the other diagram, I use a different naming for that. So here I'm calling it GPIO out. That should be called IO2 out. I mean, it doesn't matter I don't care what you call it, right? It's up to you, but I'm trying to clear up. I should have made that consistent. So GPIO out is going out to the decoders, and GPIO in is coming in from the switches. So you're going to use one or the other depending on what the immediate field is in the CSRW instruction. So if the immediate field, which I called, right here, there's a column for the immediate. Oh, wait, this is the wrong slide. Wait, hold on. Here we go. So the immediate field for these CSRW instructions is either 2 or 0. If it's 0, then I need to select the appropriate ALU source, which is input 0. So where's that at? Input 0, that's the reg select, right? And I set reg write to 1. But if I have CSRW with the hex display, that's an output, then the reg write is actually 0, and the reg selects a don't care. Because the reg selects, if you're not writing a register, no one cares what register or what you're putting into the the write port on the register file, because it's going to get ignored. You guys with me? Because if you don't write the register file, then it will ignore the data being sent into it, right? So the reg select is a don't care, reg write is 0, but there's this GPIO write enable signal. And all that does is it controls the enable on this register. This will cause the hex displays to reconfigure, to change, if that's enabled. Make sense? Where does the input of that come from, by the way? Right from the register file. From the first input of the first output of the register file, which is read data 1. Does that make sense? Now, why do we need that register there? If you don't have that register, there's nothing to lock in, to hold the values of the hex displays. The hex displays will constantly be changing, right? If you don't have that register. Yeah, exactly. Every instruction would update the hex, because basically, if you didn't have that register, the hex displays would always be showing the output of read data 1. Basically whatever's coming out of the register file, right? The contents of the RS1 register, right? So it would just be changing so fast you wouldn't be able to read it. That register is designed to basically lock in the value of the register only when you're doing that instruction that's supposed to update the hex displays. Make sense? Okay, and that's, I think, there's the whole table with all the examples. These are not all the instructions, obviously. There's only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 out of the 22. So this is about half the instructions that you'll have. Okay, and then we have a test program that you can use to test your CPU. It executes each instruction at least once, some of them multiple times. So we start out with 2 add I instructions. We add immediates to register 0. So that's what register 0 is useful for, right? It allows us to initialize constants, right? And based on that 12 and 17 value that we stick in, we can then execute all these other instructions. They all kind of feed off of that. Are these dependent? Yeah, a lot of these instructions are dependent. Like this guy multiplies into register X5 and then, actually no one uses X5.
Well, they have a couple that multiply into X4.
Yeah, that's right. X4 gets changed and then it gets written here and used here. Do we test any bypass paths here though? Oh yeah, right here. This guy, set less than, shift left logical immediate. This guy writes the register 3 and then the next instruction immediately uses register 3. So that's going to test that because when that SLLI instruction is in write back, this multiply is going to be an execute. And so you're going to be reading and writing register 3 at the same time in that case.
This is essentially like our test bench.
Right. Yeah, exactly. So you just use this to test, except what I was saying earlier is the test bench can't actually check that it's working. You have to do it manually. Yep. You just drill down in your register file and you check to see if the registers are being updated as shown here. So I have the decimal version and the hex version for each one of these. You can view the values in ModelSim in hex or decimal. It's up to you. But I've got them both there for you.
Do we write like a full test bench like we did last time?
No, well, you do, but it's just the clock and the reset. So you set up the clock in SimTop that just toggle, have the clock going, and then have the reset pulse, which is, remember the reset's active low, unless you design it to be active high, but we usually have it active low. So the reset should go low for one cycle and then high and then stay high. Yep.
This entire system is active then versus.
It's how it's just how the switches work. When you use CAD tools like the Xilinx and CAD tools and use the IP blocks, sometimes it's active, the reset's active high, sometimes it's active low. Because if it's active low, it has an underscore n after it, or just sometimes not an underscore, just an n. Means negative logic. But in this case, it's just because of the buttons, that's because of the way the buttons work on the board. Okay, and then finally, the last program you want to write is the binary to decimal conversion. Is everyone comfortable with this, how this works? So basically, you just modulo by 10 to extract the low order digit. Modulo is remainder after dividing by 10, right? Or a modulo is the remainder operation, right? And then you have to divide by 10 to delete that last digit from the value, right? And you just repeat that 8 times.
Every time you take the last one and multiply it by the power of 2 based on.
Oh no, you don't even have to do that. You just say, you take the value, you modulo by 10. So if you start out with 76 or 56, 78, you modulo it, you'll get 8, right? And then you divide it by 10, it'll strip the 8. right? So you take in the value from the switches with the so your program will begin with the CSRRW instruction. That'll take the switch value into a register, and then that value will just get whittled down digit by digit. And then every time you extract a digit, you have to insert it into another register that you'll use with another CSSR at the end to update the hex displays, right? So every time you extract one of these digits, you have to get it into another register at the appropriate spot.
And you just start by displaying the least significant on the first, and then you'd work your way up and it would display the number.
Yeah. Well, the way I do it is like when you take this 8 off, I put that in the upper 4 bits, right? And then I shift the whole thing down by 4 bits. And then I put the next digit in the upper 4 bits and then shift the whole thing down by 4 bits. So what'll happen is after 8 trips through that, after 8 times, that first digit will have started on the left-hand side, but it'll work its way down to the right-hand side at the end, right? So that's one. You don't have to do it that way. There's other ways you can do it, but that's the best way to do it if you want to take the code for each digit and copy and paste it 8 times, because we don't have a loop, and so.
So when you peel it off, it automatically puts it into, like when you peel or.
No, you'll have to peel it off after you do the modulo. It'll be that 8 will be by itself in a register. So then you could take that value and shift it 24 bits to the left. That'll put it up on the left-hand side, and then you do a bitwise OR with the kind of the output value.
Flip
it. Well, no, not to flip it, just to merge it in to the output value. It'll insert it into the output value, right? But before you do that, you have to take the output value and shift it 4 bits to the right, right? So you have this output value, and it'll start out as 0. You shift it 4 bits to the right, which does nothing, but then you put the first digit in. You shift it 4 bits to the right, you put the second digit in. You shift it 4 bits to the right, you put the third digit in. Every time you put a digit in, you're putting it into the upper 4 bits, right? So like basically what I'm saying is you consider, like you have a register, say X2 is your output register, and you're conceptualizing this as 8 slots, 8 4-bit slots. So this is 31 down to 29, right? Right, and then this is 3 down to 0. This is 7 down to 4. This is 11 down to 8. 15 down to 12. 19 down to 16, and this is going to be 24 down to 20, or 23 down to 20 rather, right? And this is going to be 28 down to 24, right? No, 28 down to 25, 23 down to 20, that's right. And then 27 down to, yes, 27. And this is actually 28, sorry. Yeah, 31 down to 28, 27 down to 21, 23 down to 20, and so on, right? So when you do the, you're going to do a multiply, mul. So you're going to have a value, like say in X3, you're going to set that up as to be 0.1, right? Which is going to be 2 to the 32nd power divided by 10, right? Which is roughly equal to 428 million actually, something, whatever. 4.2 billion divided by 10, so 428 million something, right? Make sure you round that though, because it won't be when you take 2 to the 32nd and divide it by 10, it won't be a round number. It'll be something like 0.6. So make sure you round it up, right? So then you'll take, so basically you'll do a CSRRW, and you'll take the switch value, say I use register 4 for that, and I'm going to use IO 0, right? And this register's a don't care, so I'll just say 0, right? So this instruction will take the switch value, and it'll put it into register 4, and this register is going to be ignored because it's an input. Then you'll multiply, multiply high, unsigned. You're going to multiply that 4 times that 0.1, that's in X3, and you put that in a new register like X5. right? So that's going to take whatever number came in on the switches, you multiply it by 0.1, right? And then the point, because this number is a 32 fixed point, meaning that there's 32 bits and all 32 are fractional. So when you do this multiply, you're multiplying a 32 number with 0 fractional bits times a 32-bit number with 32 fractional bits. So the result of that is going to be a 64-bit number with 32 fractional bits. So if you do a mul HU, you're basically just taking the upper 32-bit number, 32 bits, which will be the non-fractional bits of the product, right? So if you have like this number, 5678, you multiply it by 0.10, the 567 will be in the upper 32 bits of the product, and the 0.8 will be in the lower 32 bits of the product. So this mul HU is just going to extract the non-fractional bits of the product, right? So this X5 will contain the new number after you strip off.
So that would just be the 567.
5, right. But now we need that 8, right? So how do we get the 8? Well, we can also do a mul low, but there's no, yeah, mul is just mul low. And we could go X6, X4, X3.
Does it need to be unsigned as well or no?
It doesn't matter. There's no unsigned version. Whether you do a signed or unsigned only makes a difference for the upper half. So this will give us the 0.8, right? Except it's going to be, the value actually in here is going to be 0.8 as a fixed point number. So it's going to be 80% of 2 to the 32nd power. So it'll be 80% of 4.2 billion, right? So we have to get this into a regular, just as a regular digit like 8, right? So the way you can do that is you can do another mul H, U. You could take X6 and multiply it by 10. So because it'll be 0.8, you multiply 0.8 by 10, you get back to 8. And that's what we want is the 8, the remainder. So you can multiply that by another constant, let's say X7, I don't know, or X5, yeah, X7. You could set up X7 with 10. So if you multiply that by X7, you put the result of that into X8. And that 8 now will contain the 8. That's the modulo. So it's going to take 3 multiplies for every digit. You're going to have to do 3 multiplies 8 times for 8 digits. So there's going to be 24 multiplies in total for this.
You can do this in a branching statement, right?
You can't branch. You don't have branch instructions. You're going to have to copy and paste them. We're not going to have branches until next lab, the next assignment. Okay, so then once you do that, you want to get that 8 in the left-hand side. So you shift left logical immediate, X8, 28 bits? 28. I might have said 24. I meant 28. Should be 28 bits. That's going to take, so basically the 8's going to start out here, right, after you do this mul HU. And we need to get the 8 up here, right? So that shift will do that. And then you're going to have another register that will be your result. Let's call it X10, right? That'll start out initially as 0, but every time we add it, what new digit, we shift it to the left by 4 bits, right? So you shift it left by 4 bits. So you do shift right by 4 bits. Shift right logical immediate, X10, 4, and then you just do an OR. You do an OR with X10, and X8. That's going to take this 8 and it's going to stick it there, right? And then the next time you go around, it'll push the 8 over here, and then you'll put the next digit here, 7. And then the next time it'll shift the 6 here, and then the 7 here, and then the 8 here, right? So after 8 times, that 8 will start out on the left-hand side, but by the end, it'll be over on the right-hand side, right? Makes sense? So by the time you're done, you'll have 5, 6, 7, 8 will be in this case, you'll have 0, 0, 0, 0. You'll end up with 4 zeros plus the 5, 6, 7, 8 in 32 bits. And this is basically what it'll look like in hex, right? But it's not really hex, it's a binary coded decimal, because when you send this out to your hex displays, it'll actually say 5, 6, 7, 8, even though the original value would have been the binary version of that, right? Okay, so that's how the code, and like I said, this block of code will have to be copied and pasted because you don't have branches yet. Any questions? You guys okay with that? Could you see that on this side? I don't know if you can read that from on this classroom is too wide. Okay. Okay, so let's move on to the next lab then. Let's talk about branches. So I'm going to get a little ahead here, but I want to get you ready for the next lab, which will be adding the branches and jumps. So the branches use a PC relative offset. So the branches are I-type instructions, and the immediate field is used to designate where you're branching if the branch is taken. The branch is relative to the program counter, right? So it's basically, it's the number of instructions you're going to skip relative to the branch instruction if the branch is taken. You guys with me? You guys remember that from 212? But when I say relative to the current instruction, what does that really mean? Well, this is a subtlety. This is actually different. This is a difference between RISC and MIPS, the MIPS. So MIPS used to use, whenever you'd have a branch instruction in MIPS, it would calculate the branch offset relative to the instruction that's after the branch instruction. Okay, what that means is that if your offset is 0 and you take the branch, it's going to go to the next instruction, which it would have gone to anyway had the branch not been taken, right? So a branch with an offset of 0 in MIPS would be pointing to the next instruction. If, on the other hand, your offset was -1 and you take the branch, now you're in trouble because it's going to branch to itself endlessly. And there's no way, it'll create an infinite loop and there's no way to escape from it because the branch instruction is an atomic operation. There's no way that, you know, there's no chance for the branch condition to suddenly become false, right? So it'll be true forever. You guys with me on that? Right? Does it make sense? So the offset in a branch is just the number of instructions that you're going to skip, either forward or backward if the branch is taken. But in MIPS, it's relative to the next instruction, which in our case is PC fetch. Because you remember, PC fetch is the address of the instruction being fetched. So if you look at PC fetch and you look at PC instruction EX, PC fetch will actually be the address of the instruction after instruction EX. You guys with me on that? Does that make sense? So when PC fetch is 0, instruction EX is undefined, right? When PC fetch is 1, instruction EX is the contents of address 0, the first instruction. Instruction 0. You guys with me? Okay? So you might be wondering, why am I emphasizing this so much? Because in RISC-V, they changed it. In RISC-V, the branches are calculated relative to the branch instruction's address itself. So that way, if your offset is 0 in RISC-V and you take the branch, now you're in an infinite loop. And if the offset is 1, you're going to branch to the next instruction, which you would have gone to anyway had you not taken the branch. You guys with me? Now you can see that in the code here. I actually compared, top is RARS and the bottom is MARS. RARS is RISC-V, MARS is MIPS, right? And this is how they're encoded. So these branches are both branching to themselves because I typed branch to foo. You see that? Foo, colon, branch if equal foo, right? So in other words, this branch is branching to itself, right? However, if you look at the offset of the branch, in the case of RISC-V, it's 0. Right? So the offset, 0 offset means myself. Whereas in MIPS, the offset is -1. See the F's here? And the so, you know, just, this is the assembly instruction with the label foo. This is the machine instruction where the foo is translated to an offset, right? And the offset is 0 here and -1 here. Make sense? Now, why did they do that? I don't know, but it sucks because how are we going to do that? Because when we have a PC fetch, that's the address of the next instruction, right? How are we going to calculate something in the execute stage that's relative to the address of the instruction in the execute phase, which we don't even have a signal for that? All we've got is PC fetch, which is the next instruction, right? So there's a couple ways you can do that, but what I recommend is doing this. You can add a register called PCEX. So you have a PC fetch, which is the address of the instruction being fetched, which is the next instruction after the one being executed. But if you delay that by 1 cycle, you can have a version of it that's 1 cycle delayed, which you can call PCEX, which is the program counter value of the instruction in the execute stage. Make sense? Now you might say, well, wait a minute. Why can't you just? I mean, isn't it just going to be a difference of 1 all the time? PCEX will just be 1 less than PC, right? Yeah, but in order to subtract 1 from the PC and then add the result of that to the offset, you need another ALU, right? So I think it's easier to just add a register than another ALU or another adder. You don't need a whole ALU, you just need an adder, right? But you guys with me? Okay, does that make sense? It's basically a difference of 1 in the offset field, essentially, is what it boils down to. And by the way, keep in mind I'm saying 1 is 1 instruction and 2 is 2 instructions. In 212, they might have told you that you have to multiply that by 4, you know, because everything was byte addressed and instructions were 4 bytes. But in this project, we're just using word addressing for the instruction ramp, so you don't have to worry about multiplying the offset. You just use the offset directly as something you add to the PC. Okay? Okay. Any questions about that? Okay, well, here's where things get a little crazy too. The branch instructions use another type, another encoding type called the B type. You remember the, you remember in MIPS it was the, in MIPS it was what? It was the I type, right? Branches use the I type. We have an I type, right? We have an I type here. So why don't they use I type? Is it the same? I type is a 12-bit immediate, then RS1 function 3 RD opcode. Is that the same as the, is the B type and the R type the same? Immediate, 12-bit immediate, RS1, RS2, RS1 function 3 immediate opcode. Kind of, not really. Yeah, what's the difference? The branch instructions don't have an RD. You guys with me? There's no destination register. There's only 2 source registers. But they do have a 12-bit immediate. Do they? No, it's not 12 bits. It's 1 bit plus 10 down to 5 is 6, 7 bits. That's 7 bits, right? So it has a 7-bit field, and then it has a 7-bit immediate field, and then it has another immediate field down here by the opcode that's 6 bits. Does that make any sense? Well, basically, the objective is to get a 12-bit immediate, right? not a 12-bit, 10-bit immediate. There's a 10-bit immediate. You might say, why is 10-bit? You've got 13 bits there. It says 12. Sorry, 11. No, it's yeah, it is. It's 11 bits, rather. Sorry. So here's what's going on, right? In the B type, there is an immediate field. It spans two. It's actually two immediate fields that you have to put together to form the actual immediate value. But the bits are scrambled because in that immediate field, you have bit 12 concatenated with bits 10 down to 5. Right? So that's 7 bits in total, right? You got 12, which is a standalone bit, and then you've got 6 bits 10 down to 5 together. Then in that immediate field, you have 4 down to 1, which is 5 bits, right? Or actually 4 bits, rather. And then bit 11, that's concatenated to the right-hand side of that. So to reconstruct the immediate, you have to take bit 12 from there, concatenated with bit 11 from there, then bits 10 down to 5 from there, and then bits 4 down to 1 from there, right? And then that only gets you down to bit 1. What about bit 0? Bit 0 is implied to be 0. So you don't actually have the last immediate bit because you just assume it's 0. So actually what's happening there is you've got, it looks like there's 13 bits rather, but there's actually only 12 bits of total immediate bits. Sorry, I screwed that up earlier. 12 total immediate bits. But effectively, it's a 13-bit immediate because there's an implied bit at the end of 0. You guys, does it follow that? Right?
I mean, I follow. I don't know. It makes sense. It's a little.
It doesn't make sense. That's why I gave you the code for this. So here's how you decode it. So I've got 2 lines of Verilog that I gave you to use. So you've got, I call it branch offset EX. The branch offset is a concatenation of instruction bit 31, then with instruction bit 7, then instruction bits 30 down to 25, then instruction bits 11 down to 8, okay? And then with an extra 0 added, right? So this is your branch offset, which in total is 11 bits altogether, right? The problem is that that's supposed to be a byte address. And we're going to use a word address. So when you use this in your code, you have to knock off the low order 2 bits of this. You delete the low order 2 bits. Essentially, you divide by 4 and round down. Does that make sense? Because we use word addressing. And, you know, like instructions are addressed individually, not in terms of 4 byte chunks. Right? Okay, so in the branch address EX, we'll take the program counter, EX, this is the delayed program counter, this is the address of the instruction in the execute, and you add branch EX 20 down to 12. That's what's deleting the low order 2 bits, because I only go down 20 down, 12 down to 2. So bits 1 down to 0 are not included. So I'm, essentially just deleting those, dividing by 2, right? But then you might say, wait a second, what about this? What about this guy? Why is bit 12 replicated here? Well, that's because this is giving us a 13-bit offset, but our program counter is 12 bits. We have a 12-bit program counter. You guys remember that? Because remember, the instruction memory has 4,000 instructions max, 4,096 capacity. So in the log base 2 is at 12 bits, right? So the program counter is a 12-bit signal, right? So this is actually a sign extending. Because this is 12 bits, PCEX. We have to add a 12-bit to it, right? And it's assigned, this is signed offset, right? Because you could have a negative, like when you have a for loop, you branch backwards, right? For loops go up, right? So you have a negative offset, right? So this is, because it's a signed number, we have to sign extend this, right? So that's why this branch offset bit 12 is effectively copied twice. You've got it once here, and then you've got it another time in this range, 12 down to 2, right? You have to sign extend that. Make sense? Let's see. So you can use this code. I tried to work it out in these two tables, but I think it's easier just to use that because it's just so convoluted the way they set up the branch offset in RISC-V. In MIPS, it was easy. It was just the upper 16 bits. Or no, sorry, lower 16 bits in MIPS, right? Yeah, lower 16 bits. Here, it's all scrambled. Okay, any questions about that? Okay. And then it gets even weirder yet because there's also a J-type instruction that's used for the jumps. So do you guys remember what's the difference between branches and jumps? Jump is always unconditional, right? So it turns out that in MIPS you had jump and you had jump and link, right? Jump was just jump, jump and link, jump, but it also linked the return address. In RISC, there's no jump, there's only jump and link. So if you just want to do a jump without a link, use register 0 as the link address, the link register, okay? Okay, so what's the format? Well, this one's even crazier. It's an immediate field that has, and then RD and opcode. RD is your link address, link of register, rather. So what is that? RD is 5 bits, opcode is what, 7 bits? So that's 12 bits. So that means that immediate must be 20 bits. It's 20 bits, but it actually is 21 bits because you can see there's a bit 20 in there. But you can see again, though, it only goes down to bit 1. So bit 0 is being not included. So it's bits 20 down to 1, which is 20 bits, goes in. So that looks like, I mean, that's like the U-type. It's the same format as the U-type, right? But they call it J-type. But again, all these things are scrambled. So in order to figure this out, I gave you the code for this. I gave you the JAL offset and the JAL address. The JAL offset is just how far, what the offset is and the address. Now, the JAL offset is added to the PC, like the branch. It uses PC relative. Remember in MIPS, they didn't use PC relative, they used pseudo direct. You guys remember that? Now it's just PC relative again. Make sense? So you can just use that code. You don't have to try to figure it out. Okay, so let's see, what else do I have? Okay, so let me take a break and let's go back over quiz 3. You guys had quiz 3. It was due last week. So let's just go over this, make sure everyone's clear on this. The first question said, consider the RISC-V microarchitecture shown below. What's the value of reg write, ALU source EX, reg select, write back, when the following instructions are in the following pipeline stages? So we have a multiply, H, and fetch, an LUI and decode, and an XORI and write back. So we got 3 instructions in the pipeline, and the signals are the ones I have circled there, right? Reg write, reg select, ALU source. Okay, so what's reg write, write back? That is, in order to figure that out, you have to ask yourself if the instruction in the write back stage is supposed to be writing a register, right? XORI does write a register, so that should be 1. Reg select write back is asking for the instruction in the write back stage, where is it getting the data it's writing back to the register? Well, it's getting it from the ALU because the ALU does the XOR. So the reg select write back should be 2. Right? And then what's the other guy? ALU source EX. Well, now we're looking at the EX stage. So now what's in the EX stage? LUI. So what should the ALU source be for an LUI instruction? Anyone know?
Is that not like the 0 that it's pointing to? Or
LUI, well, LUI just takes the immediate and sticks it in the register. It doesn't use the ALU. So ALU sources don't care. Don't care what ALU source is. It's not doing anything with the ALU. It bypasses the ALU. In fact, it uses this mux to bypass, because as long as this mux is not, if this mux isn't set to 2, then whatever the ALU is spitting out is going to get ignored. So then you could subsequently ignore the ALU's inputs, right? So for an LUI, this mux is going to be set to 1, right? Now, I didn't ask that here. Because if I had asked what reg select EX was, the answer would be 1, but I didn't ask for that one. I asked for the write back version. So yeah, it's a don't care. I get that right? Oh, I don't have the answers here. Okay. Okay. Question 2 was, consider the RISC-V microarchitecture. What are the values of reg write, WB, ALU source EX, and reg select WB? So same ones. Different instructions. Okay, so write back is an LUI, so reg select should be 1, right? Because LUI is in write back. We're looking at reg select write back, so that should be a 1. Reg write back should also be a 1 because we're writing a register with LUI. And ALU source EX is referring to the multiply instruction. And so that multiply is an R type, so should be a 0 on that guy, right? ALU source should be 0. Okay? And then last question, or third question is same signals. In this case, we have different instructions. Write back is CSRW. So reg write, reg write WB for CSRW. Well, it depends on which CSRW we're doing, right? Yeah, right? I mean, the CSRW might write a register, or it might not. Depends what we're doing with it, right? Did I not say? I'll have to double check that. Although, I think if you do the CSRW, if you're writing the hex displays, you're going to want to set the destination register to 0. Right? That way it can't cause any damage if you set the reg write to 1. You guys with me? Now, if you go back to the examples I had of the control signals there, I had a case there where, yeah, so in this slide you can see that I set the reg write actually to 0 if I'm writing the hex displays. Right? You guys see that? Like, if I'm writing the hex displays, I don't want to write a register in my register file, right? So you could set the reg write to 0. The reg write, though, in this case depends on, you see how it depends on the immediate 12, right? So the question of whether the reg write is going to be 1 or not for CSRRW depends on what the immediate 12 is, right? Which IO I'm accessing, right? The question doesn't specify that in the quiz. However, if this were a regular RISC-V and not our RISC-V, the answer would be 1, right? Because remember I said that in regular RISC-V, the CSSR always writes a register, right? That whole thing where it doesn't write a register if you're going to the hexes is specific to our processor, right? So this question is referring to a general RISC-V processor, so the answer should be 1, right? You guys follow that, right? So if it's a regular RISC processor, not ours, that would be a 1. Reg select, well, but see, that's kind of confusing though, because I'm showing the diagram of our RISC processor, the design. But what should the reg select be for that? Well, that's going to be 0, right? The GPIO in, right? I mean, what else would it be for CSRW? And then, even though, I would only use that if if it's the keys that I was reading, right? Otherwise, I would either not write the register or I'd just set the destination to 0. Okay, in the ALU source, EX refers to the add-I. What should that be? Anyone know? Should be 1, right? Yeah, because it's an immediate, it's an I type, right? Yeah, it should be 1. Make sense? If that's clear, then it should be, you guys will have no problem with the lab, because that's basically what the lab is all about, is just setting up those control signals to reconfigure the CPU to make it execute the data paths that are needed for each instruction. Okay, how many cycles, I should say, are required to perform a write to a synchronous RAM? 1, right? Just 1 cycle, right? And what is the result from performing the RISC-V mol H instruction on input values 1111 and 0001, assuming the registers are 4 bits wide instead of 32 bits wide? This relates to this. Someone asked earlier if there's a mol U, right? Mol H. Okay, so what's going on here? We're basically multiplying -1 times 1, right? If they're signed and they're 4 bits, right? So -1 times 1 is going to be -1. So the mol H should give you what? Yeah, all 1s, right? Because it'll just be the sign bit, right? But if it was a mol HU, then we're multiplying 15 by 1, right? So the upper bits after the mol HU would be what? Would be all 0s, right?
Yeah.
Right. So if you multiply like -1 times 1, right, you're going to get -1, in which case it's going to be 111, 1111. But if you multiply, instead of -1, if you look at it as unsigned, it's going to be 15 times 1 is 15. Now you're going to have this is your high and this is your low, right? So notice that the low is the same on both, right? That's why there's no mol U. There's only a mol, because the low, it makes no difference on the low part, but the high, it makes a difference whether you're looking at 1111 as a 1 or as a -1 or a 15, right? So the answer to this question would be 1111, right?
Default is always going to be a signed bit.
Well, it's not default is 1 in the sense that there's no, it's not like mol HS versus mol H. The default is mol and then the mol U. You have to add the U if you want the unsigned variant, yeah. Okay, that's it. Okay, sounds good. I'm actually running late, sorry. We'll see you in lab on Wednesday and Friday.